So a characteristic function is a function that we use to describe some distribution, right? So if we have some random variable Psi, then we can use its characteristic function to find absolutely everything that we need, to find the expected value, to find the distribution, right? So in the same way that we used the CDF before, right? So every time we have two options. Maybe we can use the characteristic function, maybe we can use the CDF, right? And in both cases, we have all the information that we need. And if we know this, we can get this, right? If we know the characteristic function, then we can get the CDF. And if we know the CDF, then we can get the characteristic function. Why? Because if we have the CDF, for example, and if Psi is absolutely continuous, then for Psi we know that there is some PDF, right? And if we have the PDF, then the way in which we can find the characteristic function is the integral from minus infinite to plus infinite of e to the I Psi, here we have t, right? Sorry, I Psi t, yeah, and times the density. So if we know the density, we can find the characteristic function, right? Because this is just, so the characteristic function is just the expected value of e to the I Psi, sorry, we're here, x, then x, right? And this is what that is known as the Fourier transform or something like that, okay? All right? So if we know the density, we can easily find the characteristic function. If we know the characteristic function, we can find the density, all right? So there are two equivalent things. Now, we already know all the properties for the characteristic functions. We know we know that the value of the characteristic function is 0 is 1. We know that the absolute value of the characteristic function is always less or equal than 1. We know that if Psi1 and Psi2 are independent random variables, then the characteristic function of their sum is just the product, right? And many other properties that we already know, right? And using these properties, we can define whether a function is a characteristic function or not, okay? Now, why is this useful? Again, this is useful because, first of all, since we have the expected value here, right? We have the expected value on the definition, then there are many things, such as if we want to find the expected value of Psi to the k, right? This is very easy to find using the characteristic function. But also because we use the characteristic function to prove the central limit theorem. But before that, we need two more things. First, we need the theorem, uniqueness theorem. I don't know, theorem. I write like that. And so for this theorem, we have uniqueness. No, this is true. Of characteristic functions. So it means that if we have two random variables Psi and eta, and we know that the characteristic function of Psi is equal to the characteristic function of eta. So this is true if and only if the probability distribution of Psi is equal to the probability distribution of eta. So it means that Psi and eta, they have exactly the same distribution, right? So they are not equal again, don't forget. It doesn't mean that they're equal. It means that they have absolutely the same distribution, right? So if we have that for two random variables, they have the same characteristic function, then it means that they have the same distribution, right? And that is why, for example, we can find that for example, if we know that Psi has normal distribution with some parameters, right? And eta has also normal distribution with some parameters. Here we have one, right? Then we already proved before. We proved before that Psi plus eta has normal distribution with the following parameters: a1 plus a2, and sigma 1 squared plus sigma 2 squared, right? We already proved this using the density, right? Using the, so if we knew the, of course, if eta and psi are independent, we knew the density of eta, we knew the density of psi, and then we could easily prove this. Well, not easily, that's the deal, not very easy. But now we can do this easily, because we will obtain that the characteristic function of psi plus eta is exactly the same to the characteristic function of, I don't know, of alpha, where alpha has normal, okay, no, not like that, but we can forget about this. So we can find that the characteristic function of psi plus eta is equal to the characteristic function of some random variable alpha, and the characteristic function of this is going to be exactly the same of the characteristic function of a random variable with this distribution, right? So it means that this random variable has this distribution because the characteristic function is unique, okay? So it's not that we had the sum of something and we obtained that this is equal to the characteristic function of some random variable with some distribution, but this is different from this. No, it means that this has this distribution. This is because of this theorem, all right? If they coincide, then it means that they have the same distribution, right? And we are going to use that today during the seminar. Okay, we have that, the uniqueness. Now we need also, we can define the following. So yes, we have this property here. If we know that psi1 and psi2 are independent, then the characteristic function of the sum is equal to the product of the characteristic functions, right? We can actually state the following, but before that, we need to define what is the characteristic function of a vector, right? So if you remember, so psi, for example, is a vector, so it means that we have psi1, psi2, psi-n, right? We know that if psi is a random vector, then so each of these values here, the components of this vector are random variables, right? So this is a random variable, this is a random variable, and this is a random variable, right? So what is a random vector again? We already know this. A random vector is just a vector in which we have random variables, right? And now, how do we define the characteristic function of psi when psi is this vector? This is going to be just the following. So if we have that this is psi, so let's introduce also x, when x is a vector, right? x1, x2, xn, a vector, so on Rn, right? So with n components, and then we can state, well, we can write the following so that this is clear, right? So we have vectors here. The vector, this is a vector. This is going to be absolutely the same, but it's going to be like this. So the expected value of e to the I. And before we had just psi x, right? Now we need the scalar product. The scalar product we call it in English, right? So psi x. The dot product, the scalar product, I don't know how do you know that, right? So what is this? This is just the expected value of e to the I, and what do we have here? If this is the scalar product, You know what the scalar product is, right? So what do I have here? No, xi1 times x1 plus xi2 times x2, right? Xin times xn. Yes? Are you with me? Yes? Here? Okay. So this is the dot product, the scalar product. I don't know how you know it. So this is the way we defined the characteristic function of a vector, right? So before we had random variables, we knew the characteristic function of a random variable psi, and now we know how we can define the characteristic function of a vector, right? And this is useful because we can state the following theorem. This is the criteria of independence of random variables. Huh? Yes, of this random vector, right? So we know that, so we proved that before. Well, we didn't prove it. We know from previous lectures that if we have xi1, xi2, xin, then these random variables are independent if the CDF of the vector is equal to the product of the CDFs, right? And now we have almost the same. So here we have that xi1 and xi2 and xin are independent if and only if the characteristic function of this vector, right? Sorry, xi here. If the characteristic function of this vector is equal to the product from 1 to n of the characteristic function of these random variables. If this is the case, then this collection of random variables is independent, okay? And when I say independent, I mean mutually independent, of course, right? Mutually independent. So that's it. We have this. This is the first thing that we need. Okay. Now, we need something else. This is called the theorem, continuity theorem, I think. This is a vector, and these are random variables. So psi overline is just this vector, xi1, xi2, xin.
So if the components of the random vector are independent, then we can declare the characteristic function of the vector like this.
Yes. Exactly. Now, we have the next theorem, following theorem, is like this. And this is a very important theorem. I just don't know the name of this theorem in English, no idea. So let's just forget about the name and let's just state the theorem. First is that if I have a sequence of random variables, xin, right? So xi1, xi2, xi3, right? Xin. And this sequence of random variables converges in distribution to psi, right? So this sequence of random variables converges in distribution to a new random variable psi. Then the characteristic function of xin in x converges to the characteristic function of psi in x for every x from the real numbers. So if I have a sequence of random variables and this sequence of random variables converges in distribution to psi, then the characteristic functions of this convergence to these characteristic functions in every point. So now tell me, who can tell me why, and this is a very important question, why do I have this D over here, but here I don't have anything? These kind of questions are the questions that I'm going to ask you during the exam, right? Like, so this, if you know this, it means that you really understand what is going on, right? So what do I have some D here and I don't have anything here? This is what is going on. So if this, then this. Okay, so this is a sequence Psi1, Psi2, Psi n, right? So some random variable Psi. Hmm? No. Okay. Huh? Convergence in distribution means, right? So let's remember there are 4 different types of convergence. We only know 3. In distribution, what else? Almost surely. Improbability, right? So there are 3 different types of convergence. Okay, this is just one of these. So we have random variables, and we know that this random variable convergence in distribution to Psi. And then we have that these functions in every point convergence to this.
Yeah, because the characteristic function is invariant to the parameters of the distribution. It just describes the distribution, not the specific case of.
Well, maybe I don't know what exactly you mean. So look, the deal is here. What is Psi? A random variable, right? What is a random variable? It's a function. So this is a function, right? What is phi? This is the characteristic function on x. So x is some fixed value, right? So it means that we have phi, here we have x, and we are taking these points. And we are saying that, so for example, this is like this. So these points converges to phi of psi. So if this is phi of psi, then to this point. So this is a sequence of points. This is a sequence of points, and this is a sequence of functions. No? Okay. This is very important because.
What does that have to do with? I mean, I understand that, but what does that have to do with?
Because you have calculus, right? You have 1 or 2 years of calculus. You never wrote this, right? You only did like this, right? And you did it because when you study calculus, you look at some function, right? And you say, let's find the limit of this function when, if this is x1, x2, x3, right? When this tends to x, right? So xn tends to x. So these points, or for example here, we have that f of x1, f of x2, f of x3 tends to f of x. We are talking about points. So these points. So these points are converges to some point f of x. These are points. We fix x, and we are looking at points. That's what you had in calculus, right? Here, we have to write this because psi are functions. So here we are not talking about the points here. Here we are talking about the function itself. So we are saying that this function, for example, this is the first function, right? Phi of psi 1. Sorry, here we're talking about, no, not phi, but just psi 1. So for example, this is psi 1, this is psi 2, And now we are talking about the functions, how the functions are convergent to something. That is why we had to define the different types of convergence, because it's not the same talking about points than talking about functions. No? Is it clear now?
The functions can converge without the D, right?
No.
But almost surely we don't write anything in this one.
Almost surely we don't know what?
I'll check my notes, but like, suppose they don't converge in distribution, but they just converge. Like psi event converges to psi.
Yes. I mean, they converge somehow. The question is how. Here, what is the meaning of this? It means that so if x tends to x0 when the n tends to infinity, right? What is the meaning of this? It means that for every epsilon greater than 0, there exists some delta greater than 0, such that if sorry, here we have f of x and of 0, such that if x minus x0 is less than delta, then f of x minus f of x0 is less than epsilon. If this is true, then we have this. Okay? But this doesn't apply for this case because we are talking about points here, right? So the convergence is different. Again, in this one we have convergence of functions. In this one we have convergence of points. Okay? I hope it's clear. That's why we don't have to write anything. Now,
why can't you write that the characteristic function approaches characteristic function of psi? Like characteristic functions of the sequence approaches characteristic functions of psi. Why do you have to talk about this?
you mean here? Why do we have like this in this case, or?
Well, you're saying that the points converge, right?
Yeah, because we're talking about every x. For every x, for every real x, this is true, right? We have here inside x and x.
But wouldn't it mean that just the characteristic function also converges to the acoustic function? Not just, or that is what it means?
That is what it means if, in this case, if these functions convergence to this, then this converges to this in this way, right? So that's what we are talking about. But if we say that these functions converges to this, then this function converges to this, the function itself, no. Maybe yes, maybe not. Because there are the different kinds of convergence. That's a difficult question because this is functional analysis, but you have functional analysis, so you need to know this. No, you don't have this in functional analysis. Convergence of functions? No, you should. I think. I don't know. Anyway, functional analysis is the same than calculus, but you just don't use x, but you use functions. So I don't know. Anyway, so this is the first statement, and the second statement is that if we have some sequence of random variables, right? And we know that the characteristic function of these random variables converges to some function f, right? And this function is continuous in x being 0, right? So if we know that this the sequence, so for every x, right? Here we have for every x. So the characteristic functions, now we have on the other side, right? So now we are saying the characteristic functions convergence to some function. I'm not saying what function, just to some function, such that this function is continuously 0, then there exists some random variable eta such that psi n converges in distribution to eta, and the characteristic function of eta is just equal to f of x. So this is the same, but on the other direction, right? So if we know that there is this, then we don't need to know that this exists or not, right? If we know that this converges to some function, then it means that this function is then it means that there exists some random variable such that psi n converges in distribution to this random variable, and this function that we have here is actually the characteristic function of the random variable that we are talking about. Okay? So this is the second part of the statement. And this is all that we need to prove the central limit theorem. Okay, let's state the central limit theorem, and then we will prove it. Okay, we've come to one of the main. So there are maybe two. Yeah, two main results from this course. The first one, the first thing that you have to know for sure, and you have to know how to prove, is the weak law of large numbers. Okay, the weak law of large numbers. This is something that you have to know. If you don't know this, you fail. All right. So the weak law of large numbers just tell us that the expected value of psi is actually the average value, right? Average. It's not. Wait, I don't know if that's correct. Wait. Anyway, you know how to write. Don't remember. So this is the average value, right? So this is the first result. The expected value of psi is the average value of psi. This is the first thing. And the second thing is the central limit theorem, right?
The weak law of large numbers is that the expected value of psi is average.
Yeah.
Wow.
And this is very important because why do we want to know what is the expected value, the variance, and so on, if the expected value is some function that doesn't make any sense in the real world, right? And the expected value makes sense in the real world because it is the average value. So if you have somehow you have some random variable, some experiment, if you have some random variable, and you can define the expected value of this random variable, so you already found the average value. And you don't have to do 1 million experiments to find the average value. That's why this is very important, right? If you can define this, you know a lot about this random variable. If we are talking about some random variable in the real world, right? Now the central limit theorem is as follows. Well, let's take a break if we'll continue. And today, now we are going to prove that we actually don't need all of that. Well, we need it, but what I mean is that if you have enough, a large amount of these random variables, I mean, how to say? So you have psi, right? These are random variables. If you can repeat this experiment, I mean, for this random variable 1 million times, it doesn't matter the distribution that I have, because the distribution of this random variable with some things that I'm going to say is going to tend to random variable eta with normal distribution in parameters 0 and 1. So if you have some experiment, for example, you have a coin, right? And you flip this coin 1 million times, right? Of course, you know the distribution of this experiment, right? So if you say that success is 1 with probability 1 over 2 and 0 with probability 1 over 2, right? Success and failure. So you know the distribution of this psi. You know the distribution of this experiment. But if you can't repeat this experiment, if you can flip this coin 1 million times, then at the end, you will get this distribution. No matter what distribution we have for Psi, you will get this distribution somehow. And you can find the expected value of this random variable using just the values that we know for this. Okay, this is why this is very important. Okay, so now it doesn't matter what is, it doesn't matter if it's discrete, absolutely continuous, we have this. Okay, so now let me state it so that. So look, central limit theorem. We have psi 1, psi 2, psi n. This is a sequence of independent, identically distributed random variables, right? We have a sequence of independent, identically distributed random variables. And we know that, so all of them, right? Sorry, not like this, but. So we can say that for every I, psi of I has the same distribution that psi, right? So it's like having psi many times, psi, 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 psi. We just call it psi 1, psi 2, and so on, because we need like this distribution, right? And we can say that, so the expected value of psi is A, and the, sorry, not D, but, and the variance of psi is sigma squared, right? Then we can see that we can introduce the following random variable Sn. Sn is going to be the sum of these random variables, right? So we sum up everything, and then we state that Sn minus n times A over the square root of n sigma squared. This new random variable, this is a new random variable, converges in distribution to some random variable eta, and eta has normal distribution with parameters 0 and 1. This is the central limit theorem, all right? So for example, what do we have here? We have the following, look, we have that, what if psi, so psi, okay. What if psi is just a random variable? We have 1 with probability 1 over 2, and we have 0 with probability 1 over 2, right? So we flip this coin, and then we get success or failure with probability half, right? And then Sn, what is going to be Sn? Is the number of successes that we obtain, right? So Sn is the number, right? So we can now define the probability that the number of successes is less than any number that you want. So that if you flip this coin 1 million times, so this value, this random variable is going to be about, well, what do you think? Half, right? I mean, half of a million, right? So the number of successes is more or less half of the number of trials that you have. So look, what do we obtain here? We obtain Sn, so Sn minus Na. What is A? A is the expected value of Psi. What is the expected value of Psi in this case? It's 1 over 2, right? And what is the variance? What is the variance of Psi in this case? No. No. 1/4, yes. So we can multiply this by 1 over 2 and square root of n, right? So we just found it, these values now. And we say that this, so this tends in distribution to this. What does it mean that this random variable tends in distribution to this random variable? it means that the CDF of this tends to the CDF of this. So it means that the probability that this random variable is less or equal than x tends to the CDF of eta in the value x.
What do you mean by 10? Do you mean as n increases or what?
What do you mean by what?
By 10 to...
This is a number. Probability of something, this is a number. Right?
You said it tends to another number. Right?
Yes.
That means there must be some change. It tends to some other number. And the n goes to the... So is it a...
Ah, yes. Now you mean yes. And here also, of course. So it means that, what is this? What is the probability that some random variable eta, with normal distribution is less or equal than x? So this is the integral from minus infinity to x, right? Of, what do we have here? Of, well, this, right? 1 over the square root of 2 pi e to the minus t squared over 2 dt, right? So, if we want to find the probability that this number is less or equal than x, all that we have to do is to find this. And this integral is denoted like this. And of course, to find the values of this integral for different x is difficult. But in every book of probability theory and on internet, you can open the book, and in the last page, you will find the value of this integral for different values of x. So now you can solve exercises just, if you need, for example, to find this, then this is equal to this. Let's say that, for example, this is 3 here. So we need to find this, right? And the value of this is about 0.9 something. I don't know. Okay? So now let's see what is this. So this is the probability. Sorry, no, not 0.9 here, but yeah, I'm going too fast. Forget about that. We still don't have to write 3 over here. X, right? So by now we know this. So if we want to find the probability of this, all that we need to do is to find this. Now, do we need this? No, we don't care about this weird random variable. We care about this random variable, right? The number of successes that we have is n. Here we don't have the number of successes. We have the number of successes minus n over 2 over this. Now, what if I want to find the probability that, so we have Sn is between something and something, right? So what if, in this case, we have 3, right? So what if this, okay, let me write it like this. So we have again, Sn minus, what do we have there? N over 2 over, they said that we want to find the probability that this is between 3 and minus 3. Then they extend to the integral from minus 3 to 3 of this, right? Now we can do the following. What is this? We can multiply to both sides, right? So we get minus 3 here, 2 square root of n less or equal than Sn minus n over 2 less or equal than 3 and the square root of n, right? And now we can to this side to sum up, right? So we have that Sn is between n over 2 plus 3/2 of the square root of n and n over 2 minus 3/2 of the square root of n. Now this is some probability that we might want, right? This is the probability that the number of successes is between this number and this number. What if, for example, we have 1,000 here? Then what is this? So let's say that n is n 1,000, right? Then we are looking to the probability that the number of successes is between what values? 1,000 minus 3 over 2. What is the square root of 1,000? Okay, let's use 10,000, so that is easier, right? So is that this is between 500 minus 3 over 2 of 100, right? And 500 plus 3 over 2 times 100, right? We are looking at the probability that the random variable is about 500. And using this, right, we are going to find that this is about 0.9 something. So to find this, all that we have to know is this: the distribution of the normal, the CDF of the normal distribution, of the standard normal distribution. So using this, we can find the number of successes being between these two values, and it's about 0.9. So of course, with high probability, if we flip the coin 1,000 times, well, the number of successes is going to be about 400 something or 550 or something like that. Now it's clear the statement of the central limit theorem. Yeah? Okay. And now let's prove it. Now let's prove it. So the proof of central limit theorem. So this is what we have. So we need to show that this random variable converges in distribution to this random variable. What do we need to do? We need to find the characteristic function of this random variable. We need to show that the characteristic function of this random variable tends to some function, and that this function is the characteristic function of a random variable with this distribution. And using the theorem that we had before, where is that? Using, well, not this one, but using this theorem, everything will be proven, okay? So look, again, we have, this is some random variable. So this is like having psi n. And we are saying that psi n tends in distribution to eta, right? We have this. This is what we want. This is what we are looking for. This is what we need to prove. So let's find the characteristic function for every psi. Let's prove that the characteristic function for every psi tends to some function, right? Like this one. And let's show that this is the characteristic function of a random variable with distribution, with normal distribution in parameters 0 and 1. If this is true, then using this theorem that we have here, it means that we obtain this, and that's it. Okay, I hope the idea is clear. Now, not what exactly is not clear?
How are we going to prove it? So you said we were going to prove it by
Yeah, so look, what do we have here? We have that if we know that some sequence of characteristic functions tends to some function, okay, let's say some sequence of characteristic functions tends to some characteristic function, then the random variables that we have here, these random variables, tends in distribution to the random variable that of the characteristic function that we obtain. Now let's find the characteristic functions of this sequence here. So we are going to find the characteristic function of psi1, characteristic function of psi2, and so on. Let's prove that these characteristic functions tend to some function. And this function is going to be the characteristic function of a random variable eta with this distribution. Okay, now let's introduce, so we have psi I, let's introduce psi I over line. This is going to be psi I minus A, right? We can see that the expected value of psi I is 0, right? Because the expected value of psi I over line. Because the expected value of psi I, as you can see here, is A. So A minus A is 0, right? Now, what else can I do here? So we need to look at the characteristic function of this random variable, Sn minus Na over the square root of sigma square n square. I need to find this, and I need to prove again that this tends to this. This is what I want to prove. This is what I want to show. Okay? Now, what is this? This is the characteristic function, and I can change this Sn. So this is going to be the sum of psi I. So we have minus A and we have minus Na. So this is going to be just psi I from I1 to n, right? Here we have the square root of sigma square n square. N is not a square. Yes, thank you. Right? In every point x. So what is this? This is the expected value of e to the I psi, but psi is this. So this is the sum from 1 to n of psi I. And I have x, and I can divide it by this. Right? I can actually do the following right away. Like only here x over the square root of n, and here I have the square root of sigma square. Right? Now what is this? This is the characteristic function, and now I can, here I had x, but I can change this x by this. So this is going to be the characteristic function on this point, x over the square root of n, of this random variable, right? Okay, sorry if I'm going too fast. Then, what else do we need? What else do we need? Here, by the way, I forgot about the overline, and overline here. Okay. Yes, let me think. What do we know about psi I? So psi 1, psi 2, and psi n, they are independent. Right? They are independent. So we have the sum of independent random variables here. So what can I write here? So this is the product, right? So this is the product from 1 to n, right, of so we have psi I underline over the square root of sigma squared, right, in the point x over the square root of n. Okay, what can I do with this? So next, I have to remember what is e to the x, right? The Taylor's expansion of this is this 1 plus x, right? Plus x squared over 2 plus x3 over 6 and so on, right? We know this. Now, what if we have e to the I psi x? Then we obtain the following. This is going to be 1. Okay? Yes. But now we need, yeah, don't like this, but we need just this for, so the Taylor expansion of this again. So I psi x. We need it in the point 0. So this, how to say it? What is going to be this? This is, okay, f of x is a sum from 0 up to n, well, actually infinity, right? F of, so the derivative, the k derivative in the point 0, right, times x to the k over k factorial. This is the Taylor expansion, right? That you know. Now let's use this to find that, to find this. So the first value, if we have 0, then we obtain 1, right? If we have 1, then we have just the value. So if we have 1, then we if we have 1, then the first derivative is just the same. No, it's just this value. 0, 1 is going to be x, right? No, 1.0. Yeah. Then what do we have for the next one? For the next one, we have the first derivative, and the first derivative is I psi e to the I psi x, right? So this is going to be I psi, but we are looking at the point 0, so this is 1, and then I have x squared over 2, right? And if we look at the next one, this is going to be minus, because I will have I psi squared, so it's going to be, or plus I squared, right? Psi squared x like this. Now let's look at the expected value of this. It's going to be 1 plus what is the expected value? Well, just x plus I psi, no, here I x squared over 2 psi, so plus I x squared over 2, the expected value of psi, plus I squared x over 3. Why do we have x here? Because of this, right? 6, expected value of psi squared, and so on. Okay, now why do we need this? because this is what we have here. Okay, and before that, so let me move to this side. So we know that psi I, all of them have the same distribution. So this is just this. So this is equal to this. Psi, just psi. Let's say psi. Yes. To the n power, right? We are multiplying n times the same function. So this is all of this to the n power. And now, let's look at this. What is this? So this is the expected value of e to the I. And here we have psi over line over the square root of sigma square, and x, and like this, right? So what is going to be this? It's going to be v1 plus x right? Then we have next plus I, and I have x squared, x over the square root of m, everything is squared, and over 2, and the expected value of psi, the expected value of this over this, plus something else, right? Now we can put all of this inside, and what do we get? What do we get? Do we get what we need? I'm not sure. Let me verify that. So we have that, why do we have 0 here? Okay, because this, here we had, what do we have here? I to the x, this is, here we had psi already, here we have psi squared, and here we have psi, yes, like this, and here we have further psi, this is square, this is 3. Okay, now we can put this, all of this here, and what do we get? We get 1 plus. So here we have this square, and here we have the expected value of psi over line over the square root of sigma squared. Now this is 1 plus, and here is missing I, by the way, also. Then here is I squared, and here is I to the 3, right? Square. Okay, now it's okay. So, what do we have here? We have I to the, here we have x over the square root of m, right? And the expected value of this, right? Then, plus, we have I squared, right, over 2, and we have x over the square root of n squared, plus, and here we have the expected value of psi over line over the square root of sigma square. And all of this leads to O of 1 over the square root of n squared. You know what is this, right? Little o, right? Big O, little o. Okay, so this tends to 0, right? We know that. Now, what do we have here? We have the expected value of psi over line. We know that the expected value of psi over line is 0, right? What is that? The expected value of psi over line is 0. So all of this is 0. And now, what do we have here? So we obtain that all of this is equal to 1 plus, here we have minus, sorry, here we have minus, because we have I squared, minus x squared over 2n, right? And the expected value of all of this square. So was 0. I mean, let's say that's just 0, right? It's and all of this to the n power. This is what we have now. So let's look at what we have here. This, the expected value of psi over line squared. This is the expected value of, okay, we know that the variance of psi over line is equal to the expected value of psi over line squared minus the expected value of psi over line, all of this squared, right? So from here, we can get that the expected value of psi over line squared is just the variance of psi minus, sorry, plus the expected value of psi over line, all of this square. So from here, we can find the expected value of psi over line squared. What is the expected value of psi over line? This is 0, right? And what is the variance of psi over line? We know that is sigma squared, right? Because we have that psi over line is just psi minus a, so the variance doesn't change, right? And the variance of psi is sigma squared. So what do we have here? We have that this is equal to 1 minus x squared over 2n, and the expected value of this square is sigma squared over sigma squared, because we have, sigma squared, so this is sigma squared or the square root, no, sigma squared. So this is sigma squared over so wait, so this is sigma squared, and here we have this square, then this is going to be sigma squared also, and this cancels. No, wait, but if we have sigma, yes. So to the nth power. So this is 1 minus x squared over 2n to the nth power. And the question is, what is this? This tends to what? So we know that 1 plus, how is that case? X over n to the n. This tends to what? To 1? No. E to the x, right? So this tends to e to the minus x squared over 2. Yeah? And e to the minus x squared over 2, we haven't done that, but this is the characteristic function of some random variable eta, such that eta has normal distribution with parameters 0 and 1. And that's it. Questions? So from here, let me write that, right? So we can conclude by the theorem stated before that this Sn minus Na over the square root of n sigma squared, this is what we had at the beginning, right? So this, and this is what we had here, right? That this this sequence of random variables that this tends in distribution to some random variable eta, and eta has a normal distribution with parameters 0 and 1. By the theorem that we stated before. So for example, if your question for the exam is the central limit theorem, you have to know this theorem as well, right? So this one, because this is necessary for the proof. Okay, that's it. Mm-hmm. 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 No, and this is the characteristic function of this random variable. So we are going to prove in 20 minutes, right, in the seminar, that if eta has this distribution, then its characteristic function it is 1. Maybe we already did that, I don't remember. So let's see. Okay. Is it clear? So it's long, but I just got confused because I forgot about Psi here. Here. Yeah, here I forgot about this one, and of course without this, it doesn't work. So, but you just have to know the Taylor's series, and well, and actually that's it. And this property, right? And that's it.
What is this property? Was it last class?
Yeah, I think so. Yes, I don't know. Is that if you have the sum of independent random variables and you want to find, so here you have the sum of independent random variables and you want to find the characteristic function of this is just the product of all the characteristic functions. Okay, see what we have here. That's it. That's it for the theory. We are finished with theory for this semester. Okay, so let's take a break and we'll continue. homework 7 to homework 10. So, random vectors. So you have to use the convolution formula, right? Then we have expected value, yes. Different things. So the expected value for some random variables or some distributions that we have. Yeah, we can find, by the way, for example, to find the cave moment of some random variable, right? Then we have characteristic functions and central limit theorem. So these are the 4 topics that we have for the test. So we will have 6 problems, maybe 2 problems from the central limit theorem, 2 from the characteristic functions, and 1 and 1. Maybe, I don't know, let's see. Okay, so let's continue. What was the last that we did last class? I really don't remember. Yeah, but so we solved exercise 1 from homework 9 completely, right? And exercise 2, we solved it. We had the last lecture here. Yeah, I don't know. Yeah, you need to ask about that, because if you want to look at the recordings and they are not ready, so, and I don't think that they're going to be ready in 2 weeks. So. The last one, like 40 years, is usually we don't have the last lecture. Did anybody take notes? So, what was the last question that? Which one? A, B, C, D? I don't think that everything was along. Huh? And we did Poisson, geometric, and so on. Okay, let's say that we did. If we did it, that's your fault. Okay, let's do this again, right? Number 2 again, because let's see that you need it, right? Okay, over here. Characteristic function. The first characteristic function that we need to find is the characteristic function for Psi to have a Bernoulli distribution with parameter p. We know that the characteristic function of this random variable is, you can tell me? Yeah, so we know that the formula is like this. Of what? So what are the possible values for Psi? 0 and 1, right? So let's take 0, e to the 0 is 1, times 1 minus p, is 1 minus p, plus p times e to the ixc1, so e to the ixc. Is this clear for everyone? What I'm doing over here? If this is not clear, all the other things are not going to be clear. So, is this clear? No? Okay. Let's do it. So in general, if we have a discrete random variable, and this is right? So the expected value of this is just this times the probability that Psi is equal to this. So what the possible values are just 2. So psi can take only two values, 1 and 0. 1 with probability 1 over 2, sorry, 1 with probability p, and 0 with probability 1 minus p. Right? So we take k being 1, no, 0. So e to the I psi 0, so e to the I psi 0 times the probability that psi is 0 is 1 minus p. Right? This is the first value. Plus e to the I psi 1, right? And the probability that psi is 1, which is p. So we know that this is 0, sorry, this is 1, e to the 0 is 1. And we know that this is just IXC. So this is 1 minus p plus e to the IXC times p. Now is it clear? Okay, I hope it's clear. Again, if you don't understand this, you are not going to understand absolutely anything. So I hope this is clear. Now, we can talk about the binomial distribution with parameters n and p, right? So let's say that eta has binomial distribution with parameters n and p. We know that eta can be expressed as the sum of psi 1 plus psi 2 plus psi n. So eta, what is eta? Eta is the number of successes that we can obtain if we flip n coins, right? So we flip n coins and we obtain some number of successes, right? But this is exactly the same of flipping one coin n times, right? So we flip this coin here, we flip the coin again, and so on. So if eta has binomial distribution with parameters n and p, so it means that this psi 1 has a Bernoulli distribution with parameter p, this one has Bernoulli distribution with parameter p, and so on, all of them, right? So if we want to find the characteristic function of eta, since we have the theorem of uniqueness, so this is going to be exactly the same of the characteristic function of psi 1 plus psi 2 plus psi m, right? Is this clear? Now, what do we know about psi 1, psi 2, and psi n? We know that we are flipping this coin independently, right? So psi 1, psi 2, and psi n are independent random variables, right? So it means that this is equal to the product from 1 to n of phi of psi. So let's say that psi 1, psi 2, psi n, they all have the same distribution. So psi I have the same distribution that psi in T, right? But we know that, actually like this, yeah. But we know that all of them have the same distribution. So this is exactly, so multiplying this n times is phi xi to the, in the point T to the n, right? We are multiplying the same function n times. This is the same as having the function to the power of n. And this is the characteristic function of a random variable with distribution with Bernoulli distribution. And we know that the characteristic function of this is this one. So all that I need to do is to write that over here. So 1 minus p plus e to the I c p to the n. And this is the characteristic function of a random variable with binomial distribution in parameters n and p. Okay? Now, oh yeah. Okay, so now we already know about the Bernoulli binomial. Now let's find, yes, we already found that. I remember that we did. We already did this. Okay, anyway. So let's say that, number 3, let's say that theta has normal distribution with parameters 0 and 1, right? And today we use the following. We use that the characteristic function of eta should be e to the minus t squared over 2, right? Because this is the function that we obtained, so we should get this right now. So how do we obtain this? Again, so this is the characteristic function of eta in t. This is just the integral, right, from minus infinity to plus infinity of e to the I psi t, and times the density, and the density in this case is 1 over the square root of 2 pi e to the minus right. No, here x dx, sorry. What am I doing? Of course, sorry. So this is xt e minus x squared over 2 dx. Now, this is important. Don't get confused here as I just did. Here we need to get the function of t, right? But, so the definition again is this. The expected value of e to the minus e of I psi t. So this is the t that we have here, right? And we have here psi. So if we want to find the expected value of psi, of some random variable, of psi, right, we need to look at all the possible values of psi. So we are changing psi by x, right? So here we have x, and here in the density, we'll have the function on x, and we have this integral over all x, right? So don't write here t, you will get something wrong. And this is equal to the following. So this is the integral from minus infinity to plus infinity of e to the minus t squared over 2. And we will get 1 over the square root of 2 pi e to the minus minus x I t the square over 2 dx. This is exactly the same. You can check it, right? And what do we have here? So we can, this integral is on x, right? Dx. So since here we don't have x, we can apply this integral only to this side. And this integral, this is the probability density function of random variable psi, right? Where psi has normal distribution with parameters it and 1. So this is exactly the same, but we don't have 0, we have it, okay? So of course, since this is the density of some random variable, then the integral from minus infinity to plus infinity is just 1. So all of this is 1. So at the end we get e to the minus t squared over 2. And this is the characteristic function of eta, right? Very important, because we need it to prove the central limit theorem. Now, this is for the standard normal distribution, but what if we wanted to find it for any normal distribution? So let's say that psi has a normal distribution with parameters a and sigma squared. Then we know that psi has the same distribution that the square root of sigma squared times eta plus a. We know this. I say this a lot of times, right? So for example, in the exam, I can ask you to prove this. This is a good exercise to prove why this is true, right? So all that we have to do is to find, so if we want to find the characteristic function of Psi, we can find the characteristic function of this new random variable, right? And what do we get? We get, so what is this? This is the expected value of e to the I, and then I have the square root of sigma square eta plus a, and I have here t, right? I'm looking at the expected value of a random variable, right? But this is not a random variable. No, wait. Yeah, so this is not a random variable. The random variable is over here. This is the random variable eta. So I can do the following. So this is just e to the I a t, right, times the expected value of e to the I, the square root of sigma square eta t. So this is the same of having, again, we have e to the I a t. And we have the expected value of this, and this is the characteristic function of eta in the point square root of sigma square t. All right, so we can take this together, these two things together, and instead of writing t here, we just write t the square root of sigma square, right? And this is just this, and we know that the characteristic function of this is e to the minus t squared over 2. So minus sigma square t squared over 2. That's it. This is the answer, right? So we can write this little difference. So this is going to be equal e to the yeah, like this. Usually it looks like this. So this is the characteristic function of a random variable such that psi has a normal distribution with parameters a and sigma squared. And you can see that if we say that a is 0 and sigma squared is 1, then we just get e to the minus t squared over 2, right? So this. If we say that a is 0 and sigma squared is 1, then we get this. So everything is kind of okay.
That box on the first slide at the top, do we just find the random variable like that? We define it.
We say that these two random variables have the same distribution, and we prove it. I don't know. No, I think 3 weeks ago. So we found that the CDF of psi is exactly the same to the CDF of this random variable. So the CDF of this random variable is equal to the CDF of this random variable. It means that they have the same distribution. Okay. What else? Okay, we have the Poisson geometric and gamma and Cascade distribution. Poisson geometric, we already did it, I think, so I'm not going to do it again. But we can do the gamma distribution. It's going to take us time. Oh, it's okay. Gamma distribution. So, do you have any questions by now? Or is everything clear? Any questions by now? No? Okay. So we say that in this case Psi has gamma distribution with parameters alpha and lambda. I think we haven't talked about the gamma distribution, and now we will, right? Let's just let me see how it looks like. I don't remember. How does the gamma distribution look like? Is based on the gamma function, yes. Here I have it. Okay, so we say that the density of Psi in the point X is equal to the following. Is equal to. Did you know what the gamma function is? This is from calculus as well. No. Okay. So, but before, so we have the density is something like this. Let me write x to the alpha minus 1, alpha to the lambda to the alpha, e to the minus lambda x, all of this over the gamma function of alpha for all the values such that x is greater than 0. Right? Where the gamma function, it depends, right? So if gamma is an integer, then this is just alpha to the minus 1 factorial. So the gamma function is the general notion of the factorial of the factorial, right? So the gamma function of this is true if alpha is a non-negative integer. So we just take alpha minus 1 factorial, right? And if alpha is some real number, any real number, then this is the integral from 0 to plus infinity of t to the alpha minus 1 e to the minus t dt. Don't worry, you don't need to learn this by heart. You just need to know this. I mean, you just need to see this. That's it. So, what do we need to do to find the characteristic function of Psi? Well, everything is just by definition, right? So this is, again, the expected value of e to the I psi t, right? So this is the integral from minus infinite to plus infinite of what? E to the I x t times the density, so times all of this, right? So x to the alpha minus 1, x lambda to the alpha, e to the minus lambda x, all of this over gamma function alpha for the values x greater than 0 dx. So we can see that this is 0 if x is greater or is less or equal than 0, right? So it means that we have to take the integral from 0. So we can forget about this, it is going to be from 0. And that's it, right? Now we have that, and let's do the following. So let's say that we want this. So let's put all of this together. So 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 it means that we have the integral from 0 to plus infinity of e to the, what do we have? X, and we have here, let's say minus x, and we have then lambda minus it, right? And we have x to the alpha minus 1, lambda to the alpha, all of this over the gamma function of alpha dx. Now let's do the following. Let's say that y is equal to minus x minus x, so we need minus x. Yeah. Lambda minus it. Okay, so what do we have for dy? This is just, so we have dy is over, so it minus lambda, have dx. Now we can replace all of that over here. And what do we get? We get the integral from 0 to infinity of e to the minus y. Sorry, yeah, it's better if you have this. Just we need minus y, then say that this is plus over here, and then this is minus this. Okay, so e to the minus y then x, we know that x is y to the times y to the alpha minus 1 over lambda minus it to the alpha minus 1, right? This is just x to the alpha minus 1. Then alpha to the lambda, sorry, lambda to the alpha, right? And all of this over the gamma function. And I forgot about this. Yes, I forgot about this. So I have to multiply this over lambda minus it dy. Okay, what do I get here? So this is equal to, look, I can, this and this, I can put them together. So I get here lambda minus it to the alpha. And I have lambda to the alpha here. So I can lambda to the alpha here. And all of this just end 1 over the gamma function of alpha. I know that, so this is all, this is an integral over y, so this doesn't depend on y, so I can take it out. And I have here e to the minus y, y to the alpha minus 1 dy. Now if we go back a bit, so look at this function here, and look at this function here. They're the same, right? So instead of having t, we have y, and they are the same. So this function is actually, this function is the gamma function of alpha. So this cancels with this, and the result is alpha to the lambda over lambda minus lambda to the alpha, lambda minus it to the alpha. That's it. Questions? So yeah, that's the characteristic function of a random variable with gamma distribution. All right. Next. Yeah, so that's it, right? Now we can continue with exercise number 3. Let me see what do we have for that. Exercise number 3. Yeah. So we need, again, so we know that if we have two random variables with normal distribution, right, and independent, so we know that psi1 is independent from psi2. And they both have normal distribution, then the sum, right, so if both of them have, so psi1 normal distribution with parameters a sigma square, so a1 sigma 1 square, and psi2 has normal distribution with parameters a2 sigma 2 square. We already proved, right, that psi1 plus psi2 has a normal distribution, and here I have to sum up this. a1 plus a2 sigma 1 square plus sigma 2 square. And we prove it using the density. Now let's prove it using the characteristic function, right? Because I know that the characteristic function of psi1 plus psi2, since psi1 and psi2 are independent, and so it means that this is the product. That's the function of psi1, the product with the characteristic function of psi2. So what is the characteristic function of psi1? We already proved that this is, so let's find it. So yeah, here. This is the characteristic function of a random variable with this distribution, right? So all that I have to do is to write that e to the ia1t minus sigma 1 square t squared over 2 times e to the ia2t minus sigma 2 square t squared over 2. And we can easily see that this is equal to e to the I, and here I will have a1 plus a2 t minus, and now I will have sigma 1 square plus sigma 2 square t squared over 2. So the characteristic function of the sum is this, and this function is the characteristic function, so this is equal to the characteristic function of some random variable eta, the point t, where eta has the normal distribution with parameters a1 plus a2 and sigma 1 square plus sigma 2 square. So that's it, we proved, right? This takes about 1 minute, but if we do it using the density, it takes about, I don't know, 20 minutes. So of course this is much faster. So I can ask you to prove, for example, this. You can use one, I mean, you can choose the long way, right? You can choose this one. Let's say, what do you choose? What will you choose? Now, this one was for psi1 and psi2 having a normal distribution. Now let's do exactly the same, but when we have the gamma distribution, right? So let's say that psi1 and psi2 are independent. So this is exercise 2, I mean B. So psi1 and psi2 are independent, and psi1 has the gamma distribution with parameters alpha 1 and lambda, right? And psi2 has parameters alpha 2 and lambda. So the lambda is the same, alpha changes. So exactly the same, right? So the characteristic function of psi1 plus psi2 is going to be the product. So let's find the product. So let's find what is the characteristic function of this. We have it here. But it's better if we do the following. Let's divide everything by lambda to the alpha. So if we divide this by lambda to the alpha, and this by lambda to the alpha, so we get 1 over 1 minus IT, right? So we can use that here. And we obtain that this is 1 over 1 minus IT over lambda to the alpha 1 times 1 over 1 minus IT over lambda to the alpha 2. We get that this is 1 over 1 minus IT to the lambda over alpha 1 plus alpha 2. And this is the characteristic function of some eta, where eta has a distribution gamma with parameters lambda alpha 1 plus alpha 2 and lambda. Right? So we prove that if we have this, if we have this, right, then the sum psi1 plus psi2 has gamma distribution with parameters alpha 1 plus alpha 2 lambda. All right. You need a break or a break? Do you need a break? No? Okay, let's continue. Next, what do we have next? Okay, the next one is nice one. Number 4. We know how to find the characteristic function of the sum of two random variables, right? If they're independent. Now let's find the characteristic function of the product, right? So if we know psi and eta, we know that they are independent. So how do we, and we know the characteristic function of psi, we know the characteristic function of eta, and they actually have some distribution. Yeah, so psi and eta both have a standard normal distribution. So how do we find the characteristic function of the product, right? And this is what we need to do. So let's find it. Okay, so the characteristic function of the products of psi and eta what is it? So this is a new random variable, right? So if we have two random variables and we multiply these two random variables, we obtain a new random variable. So we just need to find the characteristic function of this new random variable. So e to the e to the I psi eta t. Right? And so what is this? We know that psi and eta have a standard normal distribution, right? So this is just the double integral, right? From minus infinite to plus infinite, and from minus infinite to plus infinite, of this function, e to the I xy t, right? And I have to multiply by the density of the vector, right? The density of the vector psi eta in xy dx dy. We are just finding the expected value. What do we know about psi and eta? We know that they are independent, right? So what does it mean? How do we find this? The product, right? So this is just the probability, the density of psi times the density of eta. So this is just double integral from minus infinity to plus infinity. And I have e to the I x y t. And I have 1 over the square root of 2 pi e to the minus x squared over 2 times 1 over the square root of 2 pi e to the minus y squared over 2 dx over dy. Yeah. What else? What else? What can we do? Well, we can do the following. We can have ixy minus x squared. Yeah, so we can have the following. Integral from minus infinity to plus infinite. Just a second. And then here we can write the integral from minus infinite to plus infinite. We have e to the ixy t, right? And times 1 over the square root of 2 pi e to the minus x squared over 2 dx. And here I have 1 over the square root of 2 pi e to the minus y squared over 2 dy. So I haven't changed anything, but look at this. What is this? Of what? (0.5) if in which point? No. Which one? No. No. One more chance. If you can say you have.
But I said that no distribution 0, 1.
Yeah. Yes. Y2. So this is the characteristic function of a random variable psi in the point yt. Right? Yes, a minute. I'm writing the point here. No. Right, so well, and then what? What can we do with this? So what is this equal to? We know that psi has normal distribution with parameters 0 and 1. Then what is this equal to? Look, we found that, what is it? If psi has standard normal distribution, this is the characteristic function. So we need to write this. And the only thing that we need to change is what? Yep. So this is e to the minus y squared t squared over 2. Right? So what do we get here? this is the integral from minus infinity to plus infinity of e to the minus y squared t squared over 2, right? And 1 over the square root of 2 pi e to the minus y squared over 2 dy. Now we need to solve this. How do we solve this? We just need to put together everything that we have here, right? So this is going to be 1 over the square root of 2 pi e to the minus what? Minus y squared, right? Over 2 times 1 plus t squared. Yes? Now, can anybody find this? What is this equal to? .5 points, if you can find that. You have 1 minute. Huh? Well, in general, we're looking for the characteristic function, but no. So this is some value. This is a number, something. Which one? No. Nope. I give 1 point if you can solve it. Of course it's between 0 and 1, but one point to the final exam.
That 1 plus t squared, right?
Yes, but you already have 1.5. You can get more.
I want to exceed the maximum.
I can give you 0.5 if you can do this, because you already have a lot of points. So
If I get it, can I donate my points to that?
you can sell it, right?
Yeah, exactly.
Nope. 1 point, guys. Don't say that you didn't have chance.
Is it between 0 and 0.5?
I don't know. Maybe, maybe not. Really, I don't know. It depends.
So we know it's between 0 and 1.
We're looking to the characteristic function. Of course, it's between 0 and 1, right? Well, this is positive. Yeah, this is positive. And this. No, 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 no. Maybe 1 more minute. 5 minutes. Monica and Gabriel also can participate, by the way, if you want the point. In case, just in case. Don't try to find this integral solving it. It's going to take forever. Of course not. Think about the integral that we have here. Think about this. What does it look like? No, no, it's on 1. I already told you. No. I can give you, okay, I'm going to give you a hint, but then only 0.5 points. 0.5. No, but what hint can I give you? I mean, what have we done all this time? We say, hey, we have something that looks like the density of something, right? So we try to make it such that we get a density. We change it in order to get the density. For example, sorry. for example, what we did here, right? So we had something like that, and we look at this, and no, this is a bad example. Where's a good example of this? For example, here, right? So how do we know how to solve this? No idea, but we wanted to get this, to get rid of this, right? So I don't know, it's hard to.
Maybe we can take the 1 over 2 pi out, so we're going to left with e to the power of minus y squared over 2.
And then what? Of what? Of what? Of what? Probability distribution of what? Well, maybe we get some probability distribution, but what is the random variable if we get some probability distribution? Okay, what? You are close, I think. I don't know, maybe. Okay. You need to change something. You need to change something to rearrange something here, such that you can use something that you already know.
Maybe the power itself. Maybe we have to change minus y squared over 2, 1 plus 2 squared.
So this? How? So no? That's it? Or Mihail, maybe? No, impossible. I mean, no, it's possible. You lost 1 point. What is this? Okay, no. Yeah, why not? What is this? This is the density of psi if psi has normal distribution with parameters a and sigma squared, right? Now, what is the difference between, I mean, without the integral, right? The integral is going to be 1. So what is the difference between that and this? Look, we have this. This is not good here. Right? But this, by the way, here we have sigma squared. We can say, let's say that here we have sigma squared. Then what is sigma squared if we have it? Right? So it means that now we have here sigma squared. But then we need sigma squared here as well. So we need to multiply this by sigma squared, by the square root of sigma squared, to divide it here. So we need to multiply it also here by the square root of sigma squared, the square root of 1 over 1 plus t squared. That's not very clear, right? But this is the square root of sigma squared, right? So we are dividing and multiplying. And this is what? This is the square root 1 plus t squared. And now what is this? So in the integral from minus infinity to plus infinity is 1. So the result is the square root of 1 plus t squared. Right. So as you can see here, we had something like the density, but we need to make it such that we have some value for A and we have some value for sigma squared, right? So that's it. This is the characteristic function of psi eta point T, right? Now let's solve the last one. So is it clear what I did, right? Now let's do the following. If we know that psi has an exponential distribution with parameter lambda, let's find the expected value of psi to the k. We already did this, I think. Maybe not, again, I don't remember. But we can do it using the integrals, right? I mean, we can do it using, the integral from minus infinity to plus infinity of x to the k and the density, right? But also we can do it using the characteristic functions. Why? Because we have this property that the expected value of psi to the k is just the kth derivative in the point 0 over I to the k. So if we know the characteristic function of psi, we can find the kth derivative in the point 0. We divide it by I to the k, and this is the expected value of psi to the k. We use this and we prove it, right? Now, who wants to do it, to solve it? All right. So the first thing that you need to do is to find the characteristic function for psi.
So I'm deciding that the density function for psi at point x.
Mm-hmm. And do you remember? Yes.
Well, it's the indicator function. X has to be greater than 0. Then there's
It's lambda.
Lambda e minus lambda.
Lambda e to the minus lambda.
Right.
That's it. Yeah, for all the values x greater than 0. Great.
So that's the probability density function.
Now we need to find the characteristic function of psi.
So we know that characteristic function of some random variable psi x would be the expected value of e I psi x. Okay. Now we can plug this in, or we can
using the density, right?
the integral.
Yes.
So we can straight away run the integral from minus infinite to infinite. So the expected value of this. So the expected value of this x times this.
No, yx. Don't forget, x is that's if you are looking to the expected value of psi. But you are looking to the expected value of a function of psi.
So I.
Right? So you have to know using this. So e to the I psi y, or you can change this x by t. It's better if you use t.
Which one is the ratio?
This one.
Okay, so Oh, but we have to times it by this x.
Hmm?
We have to find expected. Well, I'm just saying that like.
Yeah, yeah. So yes, exactly. So e to the I what? Xt, right? So psi, you change psi here by x.
Okay, so it's the integral for e I x t.
Mm-hmm. And now you multiply by that.
The density function.
Mm-hmm. Mm-hmm. Dx.
I'm going to remove the indicator function and change the integral. And lambda will take out. And I'll combine the exponents.
Mm-hmm.
And
Well, you have that x is common, right?
yeah, and I'll take out x.
Mm-hmm.
So it's
No, not take. Okay, yeah.
well,
Yeah, x times
x times it minus
lambda, yes. Dx.
dx.
And what is this? This integral?
Well, this is just a constant,
Yes.
so it comes down,
Mm-hmm.
and it's the same integral repeated. So this is lambda over it minus lambda
Mm-hmm.
times ex it minus lambda.
Mm-hmm. From 0 to plus infinite.
Yeah.
So what if we have 0?
If we have 0 for x, this is 0, e to the 0 is 1. We have.
Yeah, but the first is yes minus plus infinity, right?
Yeah.
Infinity.
And let me just write it first. So the infinity, e to the infinity is infinity.
Yeah, but this thing, by the way, is negative.
Oh, right, because the minus.
Yeah, we have minus in the real part. So this is negative. Okay, so we get e to the minus infinity. This is going to be 0.
Okay, so it's 0 for infinity.
Mm-hmm.
Minus lambda it minus lambda.
Uh-huh. So the result is lambda over lambda minus it, right?
Yeah.
Great. You found that. Now.
We need to find the k. Well, this is what? This is the characteristic function.
This is the characteristic function of psi. Now that you know the characteristic function, you can find this.
Yeah. So we'll write it as. I'm just going to rewrite it first.
Mm-hmm.
I'm going to plug in. I'm going to write it as this lambda minus it. Divided by. This is
I to the k.
This is I, the complex.
Yes.
I to the k.
Mm-hmm.
So let's just write out some derivatives. See what it looks like. And I mean.
Yeah, find the first one.
Yeah. So,
And the second one, and then you can see like
so phi.
some rule or something.
Phi psi 1. First derivative. We're writing with respect to t, right? Obviously.
Hmm?
But, I mean, t is our variable.
Yes, yes.
Yeah. So the first derivative is going to be lambda, and 1 over lambda minus it, the derivative.
Yeah, it's better, by the way, if you write it like this. If you write here, okay, this is going to be equal.
Yeah, 1 over.
Like this, look. It's going to be easier for you. It's the same, right? You are multiplying I. Now you can find the first derivative, which is?
The first derivative, but I was thinking this to put lambda here, or it's not gonna work. But the first derivative.
What is the first derivative? So is lambda I times what? Times this to the square root of this?
Right, the derivative of a fraction.
Yes.
Yeah. So.
Well, not the square root, but a square, right? So
I normally just use the product rule because it's easier. Just use the product rule.
Yeah, find it how is more comfortable for you.
Yeah, so it's lambda I times lambda I plus t to the minus 1. And now to find the derivative is,
lambda I is just lambda I, right?
So it's lambda I plus t minus 1. Plus. Minus. Okay, minus the derivative of this, which is, we repeat this, the bracket minus 2, times the internal function, which is 1, looks okay, and multiplied by lambda I, lambda I, right?
Why minus?
Well, the minus comes down from here.
Yeah, but you don't need this.
Well, so
because
this is the product, right? So lambda I is one thing, and this is the second thing. So this is just 1. Oh,
no, it's a 0.
Oh, right, it's 0.
Right.
Okay, so doesn't we just have this? So this is the first derivative.
Yes.
Let's find the next one.
Let's find it here.
Okay. So we have that 5 first derivative is equal to minus lambda I plus t, right? Plus t minus 1. So we need to derive this again. The minus will come down to give us plus. We rewrite the bracket.
You forgot about this. So there's going to be all of this over this to the square, right?
We can use the chain rule, the product rule again, but we don't need. We can use it. So minus lambda I plus t minus 1 plus.
No, we don't need it, right? Because the same deal. So the derivative of this is 0.
No.
Or
no. Well, is it 0 again?
Yeah, this
right,
and the derivative of this is 0.
So it's just this then. And the internal is 1, so that's that.
No, and you forgot about the. Okay. Now, in general, look, we get the following.
So, we can write the formula.
The first.
5k.
By the way, here is 2 minus 2. Here is minus 2 because you have minus 1, then you have minus 1. Minus 1, 2. Well, look, you forgot about this is 2, right? So look, yeah. So the general is.
Here's 3 then.
The general is k factorial, right? I can tell you k factorial times lambda I. Yes, times minus 1 to the k minus 1 to the k, over lambda I plus t.
Over.
Yes, over lambda I plus t to the power of k plus 1. Great. Now you know this. How do you find then this? The expected value of psi to the k is this when k is equal to 0. Sorry, when t is equal to 0. Right?
Well, that's by the
Yes.
task statement. So okay, so k is equal to 0. We can plug in k equals 0.
No, t
Oh, t. We
0.
can plug in t equals 0 first. So
The expected value. Oh, okay.
t equals 0, and then 5k equals k factorial lambda I minus 1k over lambda I k plus 1. Well, this cancels out once. So this is just minus 1k k factorial over lambda I k.
Okay, and now we can find the expected value of psi to the k. Right? So the expected value of psi to the k.
Expected value of 5.
Psi, the random variable.
Oh, right.
Psi to the k. Right? This is this over I to the k. So all that I have to do is to multiply here I to the k. So what do I get?
Well, the I to the k and this I to the k cancels out. So we will have minus 1k factorial
Over lambda to the k. Lambda to the k. And we have I to the k and I to the k. So I to the 2k.
Right, it's minus 1.
This is minus 1, so this cancels with this. And the answer is?
K factorial over lambda k.
Yes. That is the kth moment of psi if psi has exponential distribution. All right, thank you very much. So that's it, guys. See you next week for the last seminar. So next week I give you the questions